Okay, I can start. So, good afternoon, everybody. Welcome to the fifth session of the fifth Symposium of Occupant Behaviour IEA Annex 79, organized by Sustainable Energy Research Group of the University of Southampton. I am Massimiliano Manfred, and I will be chairing this session. So, first of all, I will have to give some rules. You can post your questions in the Q&A tab. Questions can be upvoted. So, of course, the questions that will have more votes will be prioritized at the end of the session, where we will have the open discussion. Please use the chat only for technical issues, or if you want to use it for general discussion, use hashtag OC20 or hashtag Annex 79. In this session, we have 6 speakers. So the first 3 speakers will have 8 minutes for presentation plus 2 minutes for question and answers, while the last 3 speakers will have just 3 minutes, and we will have the Q&A at the end of the session. So I think we can start with our first speaker, Liam O'Brien. So Liam is presenting a work related to teleworking. So, does teleworking save energy? A critical review of quantitative studies and their research methods. So, Liam, I think you can go.
Thank you very much. So hopefully you can hear or see my screen rather.
Yeah, we see you.
So thank you. So my topic very conveniently is does teleworking save energy? And this is not something I decided to start researching in the last few months. So it's just fairly coincidental. I got funding to try to answer this question about a year ago. And so far I've done a pretty comprehensive literature review, and I've written something like 20,000 words, because there's been a lot of work on this topic in the last 4 decades or so, believe it or not. 1975 was when telework started getting discussed. And what I'd like to do here is really synthesize the results for you. So I think most people assume that teleworking does save energy, and we think about driving and lack of driving if we work from home. But what I've learned, and not surprisingly, is that it's much more complicated than that. So I'm going to look at 4 main domains. So they are transportation, which is the obvious one, but then as for buildings people, we're also interested in office buildings, homes, and ICT, so basically internet that enables telework. So these are the 4 domains I'm going to look at, and my sort of concept is that we should be able to add up all of these 4 domains. So let me just explain the idea here. So if you imagine teleworking has somewhere between 0 impact, which actually it may have worse than 0 impact, but that's a line I drew. And then there's some maximum potential, which is sort of the ideal, theoretically perfect telework situation where someone doesn't drive to work, they don't have an office, they don't use any extra energy at home, and they don't do a lot of data heavy applications like teleconferencing all day and cloud computing and things like that. So most people, and most of the optimistic literature, focuses on transportation and on office energy savings. The idea is you don't work, you don't drive, and you don't have an office. Or if you're not in your office, then your office building doesn't use any energy. But then there's all the rebound effects. So these are all the red bars here that a lot of the literature is very quick to point out. Things like, if you're not in your office, well, your office is probably still being lit, ventilated, heated, cooled, etc., especially for centrally controlled buildings. Your home office now consumes more energy, and in fact, maybe when you're at home, you start cooking and who knows, doing laundry and heating your whole house and so on. There's added transportation, which a lot of people don't think about, but I'll get into that. There's the ICT needed to communicate with other people because you're isolated. And the net savings is probably much, much smaller than the total potential because of all these rebound effects. And in fact, a lot of the literature, not a lot, some papers even suggest that teleworking uses more energy than more conventional working arrangements. So 24 studies have tried to quantify one or more domains of this, well, 24 in my view credible papers. None of them have looked at all 4 of the domains. So that's sort of what I wanted to understand. So I'm as interested in the methods as the actual results. Okay, so when we do studies like this, it's really important to think about 2 scopes and boundaries. One is the temporal, one is the spatial. So this is more for my study, what I'm going to be doing, but I'm looking again at these 4 domains. Of course, there's other impacts, like we might eat more when we work at home. But that's certainly my case, probably drink more as well. But I'm not looking at those things. It's assumed same calorie consumption and so on. But the interesting thing is that the literature says we really need to look pretty far ahead because while we may choose to telework on a given day that morning or maybe that week, urban form and purchasing decisions can take decades. So I'll explain what I mean in a minute. So I'm going to look at each of the 4 domains in one slide. Clearly not enough time to look in detail. So transportation, probably the biggest energy savings opportunity, but that depends if people are driving. If people are walking, clearly it's not much of an opportunity. 3 of the 21 studies I found actually reported an increase in energy use. So what are some of the big rebound effects? People who telework don't have as many opportunities to trip change, so it's harder to pick up kids, groceries, etc. So those are now separate trips. If you telework and you work from home, that means that your family now has a car that they wouldn't have necessarily had before. You're more likely to buy bigger cars, more cars. You're more likely to contribute to suburban sprawl or urban sprawl because now you have less incentive to live close to your workplace. And on the bigger scale, if you create less traffic because you don't drive to work, then there's going to be more driving by others, or so the theory would say, because now there's more road space. The other really interesting debate that many people have discussed, and I think the jury's still out, is which comes first? Do teleworkers start moving further away from their work, or do suburbanites and people who live far from work start teleworking more? And clearly, we hope that it's the second one, but it seems to be a bit of both. In the office, well, we might assume that if you're not there, then you're not using lighting, heating, ventilation, and so on. We know that that's not really true. So I think the benefit is relatively minor unless there's a coordinated effort to really consolidate space and control spaces much more efficiently. So if we have demand control ventilation, occupancy-based lighting, electronics that go into sleep mode, and ideally some kind of hoteling or hot desking, which means that people don't have dedicated spaces, such that if we have teleworking in a systematic way, we can actually reduce the office space. These are things that could contribute to greater improvement. At home, I have a picture of a furnace here because at least in North America, most homes are controlled centrally, which means even if you're working in one small office that's 5% of your home, you need to run the furnace or the air conditioning for the whole house. Very inefficient. So the estimates for how much energy use you use if you telework range by a factor of 200. But this is highly dependent on zoning, and there's also some interesting things like if you telework, you may shift some of your loads actually during the day. Like I've started doing laundry during the day, admittedly, or my wife has, we both have. And there's some indication that big people have bigger homes, which leads to more energy use. On the ICT front, obviously there's a negative effect from teleworking. but I don't think it's very big. So internet overall uses 5 to 10% of global electricity, but much of that is not for teleworking, or it may happen anyway. And just for perspective, 1 kilowatt hour of electricity allows us to watch 4 days of Netflix just for the data transmission, or about 15 kilometers of electric vehicle driving. So I think it's pretty small compared to the transportation piece. And the electricity intensity of data transmission is dropping rapidly. So 4 methods were looked at. I don't think I have time to go into these in detail, but
can you please proceed to the conclusion?
Yeah,
just
for sure. Yeah, so I reviewed. Thank you. I reviewed methods, and they all obviously all have strengths and weaknesses. This will be in the lit review. So I guess I'll end on this slide. The verdict is that most papers determined there is energy savings potential. And these are in order of net savings, but it's notable that as things progress, the estimates are getting worse and worse, as in a positive impact, which means more energy use. Thank you.
Okay. So we don't have questions from the audience, but I have a couple of questions. So the slide where you were presenting the, now we have a question. Has anyone looked at the embodied energy of home office furniture, duplication of equipment between home and office, etc.?
Not very much. There may have been 1 or 2 papers, and my scope is more on the operational side. Yeah, there's been a little bit of sort of life cycle analysis work, really not very much.
Yeah.
Certainly it's a problem.
Yeah, I have a couple of questions because in the verdict that you were presenting, there were different studies, and essentially, do you know if there's been a systematic review comparing the methodologies that they use in the background to estimate those quantities? So I don't think there is a kind of general established rule, so it's kind of even difficult to compare the data.
Yeah, I can tell you it's the Wild West, and as someone who knows about buildings more than transportation, the buildings part is especially handled very, very poorly. So is there a review? Hopefully in a few months, because my paper is being submitted. Yeah.
Okay, then we have some other questions. Why do you think the energy gain estimates of teleworking have been getting worse over time?
So I don't think that things are getting worse. I think people are realizing all these rebound effects, and so they're starting to incorporate them. The first paper by kind of the grandfather of teleworking research, Jack Nils, really neglected the office piece and I think the home piece. And he was really advocating for telework. So he admittedly may have been a bit biased. And so, yeah, like I said, we're starting to incorporate all these things.
Okay. So I think we have time for just another questions, and then we can move the other question in the end session, because otherwise we lose too much time. So Liam, have you already, or there is a plan for you to begin tracking the activity of teleworkers to compare these models? If so, how would one participate in the study?
Yeah, so we're starting to set up a pilot study. You're welcome to participate, Jason. What we're trying to do is really measure all the major impacts in various ways. And that's proving to be quite challenging. But for example, we're looking at Google timeline data. We're installing plug load meters, temperature sensors, and so on. And we're hoping to do this for a year and pair that with some surveys.
Okay. We have still a couple of questions, but we prefer if we answer to them later on in the final discussion.
Sounds good. Thank you.
Yeah, so let's move to the second presenter. Our second presenter is Alan Wang, and he's presenting a systematic approach to preserve privacy in smart buildings. So Alan, can you please show us your screen? Yes, okay, it works.
Can you guys see it?
So you can go, you have 8 minutes.
All right, so good morning, afternoon, and maybe evening. My name is Alan Wang, and I'm a PhD student at the University of Virginia, working with Professor Hidarian. And today I'm here to talk about some of the things that we're doing to protect user privacy in our occupant behavior tracking infrastructure. And motivation and background, I think most of us are here because we agree that the study of occupant behavior is important. And while we were setting up this infrastructure, however, we got a lot of comments about people concerned with their privacy. And so what I'm going to talk about today is then first summarize our efforts to date about setting up our infrastructure, and then dive into more details as to what steps we're taking to protect the user's privacy. And as we presented in the previous annexes, we have a living link lab infrastructure, and we're collecting longitudinal, environmental, and human data. There's around 150 residents in the area and 170,000 square foot space. And this is kind of the framework. You see there's like environmental data being collected to an edge device as well as human data. And we automated a lot of these things, and there's also a user interface piece to this that we'll show you guys in the later slides. So to date, we have over 200 environmental sensors installed and marked in physical as well as virtual space. And they collect a wide range of information from occupancy to light level or appliance level energy consumption. And for human sensors, we have smart wearables, as well as we're moving to pipeline the webcam data. And there's a lot of different aspects of it, but for simplicity, for this talk, we'll walk through examples mainly relating to webcams. Here's a user interface system. So essentially, users can just sign in and see their data. And they don't see all of the data in the space, only see data that's specifically associated to them. They can see kind of historical information as well as current real-time information. And it also gives access to this survey. So if we want to do more qualitative data collection, that piece is there as well. And not only that, they can see the individual sensors in case there's maintenance requests, and they can also change their device settings in this web platform as well. And what this allows us to do is these privacy settings can then be downloaded onto an actuator, Raspberry Pi, or Jetson, where they can use to say alter the rate of collection for videos. An example would be, let's say you collect as one image per minute as opposed to rolling on webcam. And our research question. So what can we do to protect user privacy in a longitudinal system? And how might we put the burden on the system to preserve the privacy for the user? And we want to look into this a lot because many of the researches and apps that we looked at default their settings to collect the maximum amount of information from the user as possible. But for us, we're also living with the residents there in the lab. So we want to see, we probably can't keep that default setting on for a very long time. And want to see what we can do to maintain our research objectives while minimizing the user's data exposure. And our methodology is fairly straightforward. So we call it passive privacy control. It's passive because the user doesn't have to be active to maintain it. And it consists of two filter steps. The first filter step is on the part before the data reaches the cloud database, and the second was when data is being retrieved from that database. And the first thing we call privacy preference downscoping, and the second we call privacy filters, but we'll go into more details as to what those are. For privacy preference downscoping, so each device can only identify the users associated to that device. And this is important because even if user A and user B are part of the system, only user A's webcam, for instance, can see user A and user B's webcam cannot. And so if a user is identified in a view, then we can use techniques like face hashing to identify the user and use the privacy setting of that user for data collection. And if the user is unidentified, for instance, user B is in user A's webcam, then we default to the most private setting, which is off. And an example where they're both in, for instance, if user A is constantly on and user B is 1 picture per minute, then you'll downgrade it to a 1 picture per minute scope for that webcam. For privacy filters, we have hierarchical filtering as well as research-oriented data resolution filtering. For hierarchical filtering, we have access to the organizational chart of our lab. And so an example would be that my advisor, by default, would not have access to my data unless I share it. And for research-oriented data, that's probably going to be more manual. What we have to do is we have to see, for instance, what the study is on. So if it's, say, like a day-to-day energy consumption study, they might not need physiological data of the user. And for these are works that it's kind of ongoing that we're trying to work on. So find ways to encode user identifier. So besides trying to identify user space, I think there's also really good possibility that, let's say, someone's shirt is inside the webcam view. And so what are things that we can do to track that the user is present and eliminate that or protect the user's privacy? And there's also, let's see, assess the difference in data collected with and without these passive privacy controls. So an example would be like, hey, how actually effective is this in reducing information collected and how much information is being leaked at the current moment? And we also want to see the impact of different modalities of data. So is there a way we can combine different types of information to reduce the overall sampling time across the board, and also preferences of people for privacy? So is there different socioeconomic, cultural, and nationality factors that might change people's privacy preferences? And future work, the broad scope is that we want to reduce the total amount of information collected while maintaining the system efficiency. And then what we're going to work on further is identify the trust that the user has in the system via if they can see how much information we're collecting, where the data is being used and how it's being used, as well as rewards like monetary compensation or goal-oriented tracking that might help with that. And with that, my email is there. My advisor's email is also there. So
okay.
Thank you.
Thank you very much for your presentation. So we have a question from the audience. Do you have an experience data to quantify how often the participants look at the data you provide? Is there a decay from the first installment, and yes, how fast it is? So are people more engaged first and then they start to reduce the use of this tool?
That is a really good question, and that's actually one of the things that we're going to look at in the future. Right now, setting up the pipeline so that the users have access to, let's say, the video information, because that's not displayed in the same way that normal, let's say, temperature information is being displayed. So we're still setting up the pipeline for the video infrastructure.
Okay. Yeah, we have another question. Could you clarify what kinds of data are you collecting from the webcams about the users?
So our vision, at least, besides collecting, let's say, Face ID and hashing the information, we also looked at emotions. So, you know, there's like software called Affectiva. It shows the different range, valence, engagement, and a normal 5. And then I think as we move forward, there's a lot of information that can be extracted from a webcam. So if we are going to collect it, we will set it as a virtual device, and then we'll also have to get IRB approval for that.
Okay. So then we have a comment. Maybe we can discuss this in the final discussion part. So I have a question. I was interested because you were saying that essentially for energy monitoring purpose, you don't need such level of detail of data, so you can accept something more concentrated in terms of information, so you don't need to have this level of detail. So are you aware of any studies which are discussing this topic and they are discussing it from the point of view of measurement and verification, energy management, and so on?
So the Annex actually came out with a great book, Exploring Occupant Behaviors. And in there, there's multiple chapters, but one of the chapters, I think it was chapter 2, actually has a table for explaining the different types of data and the relationship that might have correlations with it. So an example could be occupancy with light level. So there's like the light switch model, but there's also studies about how temperature can affect, let's say, closing levels and vice versa. So yeah, it's a great table.
But you use the aggregated information, not the punctual one for each one.
So yeah, that was mostly a comment about, let's say, if you're doing like a day-to-day or a week-by-week analysis, you might not need like minute-by-minute information, especially if you like heart rate, for instance. If you're doing a study on energy consumption that's not related to heart rate, you might not need it. But if you're doing, let's say, behavior tracking based on emotions, you probably need more data there. So.
Oh, okay. Finally, we have another questions, and then we can jump to the next speaker. How do you communicate to the user which kind of implication there might be for sharing a piece of sensor data? The implication of sharing. So how do you communicate the problem of sharing this data with someone else, third parties?
Yeah, so there's also efforts from our lab that we're working on that I guess there's like a history of information as well. And so compensating users when their data is being used and allowing portals of access so users can delete their information, as well as being straightforward in communicating with them about like the data we're collecting beforehand. So I think IRB requires us to let the users know to the degree of the research required what we're doing with the data and what data is being collected. And so they could choose they get to see what we're collecting, but also they can opt out of the system at any time. So yeah, I think it's a valid question though, because it's, as some of the questions were mentioning earlier, there's kind of like a starting interest in the amount of information being shared, and over time, maybe people lose interest and stop caring about information being collected.
Okay, I think we can go to our next speaker, Victoria Aragon. Victoria, are you here?
Hey, yes, can you hear me?
Yeah, we can see your screen.
Okay, so let's put it on presentation mode.
A study called Understanding New Technology and Their Impacts on Your Occupants. So please.
That's correct. Thank you, Max. So hi, welcome. I'm Victoria Aragon from the University of Southampton. And I would like to present a preliminary study that we have done on understanding the impact of new technology on occupants. So this work is based on a case study, which is a care home located in the UK, in the city of Portsmouth. And this care home has about 80 flats. We have been monitoring this building as part of a EU project called Thermos, and we've been monitoring the energy demand in the building as well as the indoor temperatures in 10 flats for about 2 years. And also as part of this project, we installed smart thermostatic valves. So this is the new technology that we are talking about in this analysis. and this took part in the entire building. And so we are looking to see what the impact of this technology was, and if there was an impact, what this related to technology efficiency, to the technology itself, or was it due to user behavior, and was there any change in the user behavior at all? So to understand the potential of residents adopting this technology, we have to look at both the characteristics of the valves and the residents. In relation to the valves, in terms of usefulness, the main characteristic of the valve that is, that as a user it will be beneficial, is that you can select your desired temperature, which is different to what they had before in the building. As you can see in the picture, they had just manual on-off valves. So the only options they had before were to have the valve fully open or fully closed. And the valves are the only control that people have in their flats. There are no thermostats, so this is their only option to control the temperature in the flat. In terms of ease of use of this technology, mainly they rely on visibility, because you have to be able to look at the screen. That is the only indication of the temperature. And one particular feature is that they don't have any mechanical maximum or minimum. So you can scroll the cap and you're rotated to lower or increase your temperature, but it doesn't have a stop. So even if you reach the minimum or maximum in the screen and you see the number doesn't move anymore, you can still keep rotating the cap, which can be a bit confusing. Now, regarding the residents, these are, because it's a care home, so these are all elderly, and many people will have visual or cognitive impairments, and they rely on carers or nurses. And as you would expect for these demographics, they are not keen on using new technology, and most of the time they do not trust anything that they are not used to. So introducing something new, it's always very difficult within this building. And one thing to keep in mind is that residents did not choose to have the valves upgraded. So this decision, as you would expect, comes from to choose the technology and to do the upgrade comes from the building management and from our project ourselves, but they didn't have any say on whether they wanted this or not. So what happened when the valves were installed in January 2019? The initial reaction, as you would expect, was not good. Most residents were unhappy. They were complaining that they couldn't see the screen because there was not enough light, or that they didn't know how to rotate it, whether upwards or downwards. It was very confusing. So they were making a lot of calls to the staff, and obviously the staff had to come and help them, and it was a lot of work and extra effort for them. Because of this, and considering the main complaints that we received, last December, we took the initiative to add labels to the valves, as you can see in the picture in the bottom, in the hopes that this would make it easier for people to use them. So even if they cannot see the screen properly or the number, they still have an indication of how to use the valve. Now, in terms of the impact of the technology, the first thing we did was looking at the building energy demand. So here we can see gas usage versus heating degree days. The building is divided in 2 blocks, so this is why we have 2 plots for the north block and the south block. And the data, so far the data points in red, which are after the installation of the TRVs, suggest that there is somehow a reduction in the gas demand, particularly for the south block. This was initially good news. So, because after receiving the bad news that residents did not like this technology, this was always clearly a good piece of news. Also, I'm only showing the data from January to June, because in July there was a major upgrade in both of the plant rooms. So this period are the only months that we see the impact of the valves alone, and not in combination with other upgrades. Now, after looking at the building gas demand, we moved into looking at the indoor temperature from the 10 flats that we were monitoring. So here we can see the temperature in the lounges during what we consider to be the heating season. So this is October to April, before and after the installation of the valves. So in the before scenario, in the after scenario, it shows a higher slope. So this could be due to residents being able to choose the temperature instead of having the radiators fully on or fully closed. So it might seem that people are more reactive to weather in this after scenario. If we look more at detail at what happened inside of each flat, so these are daily temperature profiles. So it's the temperature range for each hour of the day in each flat during the same period, October to April, that I was showing before. And the main thing that we can see is that for each flat, there has not been much of a change in both the mean hourly temperatures and the shape of the profile. Now, this is good in the sense that it seems that people are still able to heat their house to the temperature that they were used to, which contradicts one of the main complaints that they were having of saying, this doesn't work as the previous equipment. What we do see is a change in the range temperature for each hour. So we could assume that a higher range in the temperature means that that person is interacting with the valve. So they are turning it on and off. So we would assume that these two flats, for example, we show a higher range are people that are interacting with the valves. So for example, when we look for these two flats at the set point, because from the smart thermostatic valves, one of the characteristics that they have is that we can read information from the valve. So we can read the set point, the temperature in the ambient temperature, the temperature of the water that comes in, and also how open or how closed the valve. So in this graph, I'm showing the ambient temperature, the set point temperature, and the outdoor temperature. And we can see that for both of these flats, the set point temperature remains constant. Now, obviously, I'm only showing 1 week here, but when we look at the entire heating season, both these flats, which initially we assumed that it was people that were turning on and off the valves, now they were only interacting maybe once a month with the valves at all. So in this case, for example, could it be that these two people were residents that were not able to reach their comfort temperature before, so they were constantly interacting and too hot, too cold, on and off all the time, whereas now they can easily select the temperature and just leave the set point as they desire. And for example, if we look at other flat where the range also varied, but initially was also small, we can see different things happening. So here, there's the same thing. If we are looking at the set point selection, the indoor temperature, and the outdoor temperature, this person, we can see that as for the set point, they clearly follow a pattern that in the morning, they open the valves at maximum, and in the afternoon, they close the valves completely. So they only use the set points in the maximum and in the minimum. So for this person, for example, we would assume that is somebody that has translated directly their behavior to the new technology and does not understand how this new technology works, that there's a set point and they can just select the temperature that they want. One thing
Victoria, can you please proceed to the
Yes,
conclusion?
of course. So just to conclude, we have seen that this technology had a very difficult adaptation from the residents, as we expect from the initial analysis. And in terms of occupant behavior, we have seen an impact in the indoor temperatures. There's much more analysis to do in terms of comfort of people and whether there's actually have been a change in the behavior, or are people taking their behavior or continuing or changing. Obviously, much more analysis with the data sets of the set points from the 80 flats. One thing also we could do is to look at whether there was any change after we installed the labels in December. So thank you very much.
Okay, we have a couple of questions from the audience. So the first one is, how long did it take the residents to use the thermostats by themselves, or did the caretakers were in charge of temperature adjustments all of the time?
So it differs by case. For example, the 10 flats that I'm showing are all people that were able to give consent for us to go into the flats because we do thermal comfort service and so on. So these 10 participants are people that are very well, they take care of themselves. Most of the time, they don't need a carer or a nurse or anyone. So for these people, it was it was difficult to understand how it worked, but they were able to see the screen and to understand what was going on. For other people, they still rely on having a nurse coming on and doing the heating. And for others, there was also a medium scenario where it took them time. And many people, when we went into the flats to put the labels, now we explain again, and they were like, okay, now I understand. But it really differs in each case.
Okay. So then there is another question, which is there a chance that residents or carers have maxed out the set points after complaints and left it to the max constantly? Also, I have a similar question because the temperature inside was extremely high. So I think on average it was 25 degrees or something. So
yeah,
they have extremely large temperature ranges, but even the average is very high. So they are overheating the house basically.
But this is something that we, at least in the care homes that we've analyzed, this is something that always happens, having a higher indoor temperature. But regarding to the question, so if carers max out the site point, this is possible, but carers, they do understand how the valves work. So for example, besides in the flats, there are radiators in the hallways and all the common areas. And all of these, which are managed by the carers or the nurses in the building, are in 21, 22 degrees. Obviously, if the resident in one flat ask that is too cold in here, they were complaining, then it's possible that they just put it at maximum. But in the flats that we are monitoring, it's very unlikely that there will be a carer coming every morning and turning it on and off.
Okay, so there was another question on energy impact, but I think we can move it to the final session. I will take this last one. What do you think about TRVs as interface between user and system in the context of the idea behind TRVs? So I think the idea is if they work correctly according to the principle for what they are designed for, maybe if I interpret correctly.
Yeah, well, I think particularly there were two things regarding the TRV themselves. First is that most people are used to standard TRVs and not smart TRVs. So I think it's very easy for someone to understand the 1, 2, 3, 4. So everybody's comfortable with that technology. Whereas I would personally prefer to see something that gives me an indication of the temperature. So I would much rather have with a TRV with a screen that tells me this. I think the adaptation, it is very difficult. So this is the main problem that I see. Is not so much that the usual TRVs are fantastic as an interaction between the user and the system, but I think because we are so used to that and it's very common, then it's just the most preferred method.
Okay, I will move the questions for the final discussion so that we can proceed to our fourth speaker. Our first speaker. So our first speaker is Jean Rouleau. He's presenting towards low energy housing in Canada and Canadian North from an occupant-centric perspective. So just keep in mind that you have just 3 minutes, so you have to run a little bit. Thank you very much.
You can see my screen?
Yeah, we can see you.
Okay, great. So today I'll talk to you about our current research project that are starting concerning occupant behavior in residential buildings in the north of Canada. So the north of Canada is divided in 5 regions, and Nunavik is one of them. It's the green one on the map. And it is a region where we are focusing most of our work on.
Sorry to comment, we can only see a section of your screen, so we can see the full...
It's not, it's just half of the screen.
Okay, you cannot see the...
So maybe if you stop sharing and start again. There we go.
Oh, yeah. Okay, great. So as I said, we are focusing most of our work on Nunavik with the green part on the map. And Nunavik is 90% inhabited by Inuit people. So we are interested to see if the difference in cultural preference and different lifestyle can lead to a difference in the occupant behavior in buildings. Of course, the north of Canada is also a very, very cold place. As you can see here on the table, which compare the climate of Quaqtak, which is one of the communities in Nunavik, with the climates of northern European cities that are located at similar latitude. And you can see that Quaqtak is much, much colder. And this very cold climate leads to space heating demand in buildings that are quite large. In fact, can go to something up to like 300 kilowatt hour per square meters. We are interested to see how impactful occupant behavior can be in buildings that already have such high space heating demand. So we gathered 3 years of data that comes from 12 different dwellings, and we are currently analyzing that data. We are planning to convey surveys, structure interviews, and to organize workshops with Inuit occupants to better understand their feeling regarding occupant behavior in buildings and how they perceive energy. And we are also planning to combine our monitor data with energy simulation. I have some very, very preliminary results for you that comes from 2 of the 12 dwellings. Unfortunately, there was a delay with the 10 remaining dwellings, and we didn't have time to fully analyze that data yet. But from what we saw from the 2 dwellings, we made a comparison between these 2 dwellings in Quaqtak with data that we previously had from the 40 dwelling buildings located in Quebec City, which is located in the south of Canada. And we made it, our comparison showed that there was a difference of behavior between the people in Quaqtak and people in Quebec City. For example, on the left-hand side of the slide, the window opening behavior, each judge represents the window opening behavior of the 2 dwellings that was monitored, and the gray shape represents the whole range of behavior observed in the 40 dwellings in Quebec City. As you can see, there is one of the dwellings that has tendency to leave the windows open more often than what we saw in Quebec City. And same thing for domestic hot water consumption. There was a difference between the people in Quaqtak and people in Quebec City. As you can see, people in Quaqtak consume about half of what people in our sample of Quebec City consume. There's quite a big difference. Now, of course, the samples are very small. It is impossible to make any statistical conclusion yet, but we are eager to see, as we are adding the 10 remaining dwellings, if this trends of difference between in behavior are still there or not. That's it. Thank you.
Thank you very much for your presentation. So we have our 5th speaker, Maareva Payet. She is presenting user behavior in low environmental impact buildings in tropical climates. So can you please share?
Can you hear me?
You see your screen? Yeah. You see your screen?
Okay. Hi, everybody. I will try to speak as clear as possible with my French accent. I'm a PhD student at the University of La Réunion. La Réunion is a French island located in the Indian Ocean on the right side of Madagascar. And in tropical climate, we are interested in summer issues. And because of the global warming situation, this context could concern more geographic areas in the coming years. The temperatures are quite constant and warm every time. The climate is tempered by important winds. And this allows the development of bioclimatic buildings. There is poor feedback on user behavior in naturally ventilated buildings in tropical climates, so their impact is often poorly estimated by designers. Our buildings have changed over the years. Initially based on vernacular architecture, they become in the 90s closed boxes using air conditioning. And today, the main challenge for tropical climates is to reduce air conditioning, which represents about 50% of the building consumption. And to do that, we build mixed mode buildings, which operate according to the outdoor climate. We can use sun shading system, vegetation, or cross natural ventilation. The louvers are manually adjustable. According to the climate, natural ventilation alone can be used, or it can be also combined with ceiling fans or air conditioning for the hottest days.
Okay.
So the questions were how to define new user for these mixed mode buildings, and when will they switch between the different operating modes. So to understand that, we are trying to model these users based on data collected on 2 buildings. Statistical analysis will describe the data in order to identify the key factors impacting on actions. And the next step will be to use probabilistic techniques to model behaviors and then to integrate them in simulation software. The user presence will be modeling using Markov chains, and action on louvers, ceiling fans, and air conditioning will be modeling using Bayesian networks. Okay, so data collection is in progress on 2 buildings, 2 non-residential buildings. We collect indoor and outdoor data like the air temperature or wind speeds. And in the same time, users' actions thanks to the real-time consumption by end use, for example, air cooling or ceiling fans, and the louvers states using connected sensor. And to conclude, we hope that a database on more tropical buildings will be created to better predict consumptions. Thank you.
Okay, thank you very much for your presentation. So we have our 6th speaker. So Namika with N-Gage sensing in multi-class in class multidimensional learning engagement in the wild. Please.
Hello everyone. Today I will mainly talk about my recent research sensing in-class multidimensional learning engagement in the wild. First, what is student engagement? Student engagement may include the emotional engagement, cognitive engagement, and behavior engagement. As reported, almost 40 to 60% of high school students are disengaged, which may contribute to low academic performance, low disaffection, and high drop-off rates. So my research question is, can we infer student emotional, cognitive, and behavior engagement from physiological and environmental data? And therefore, I collected a data set last year in a private high school in Melbourne. I collected environmental data, wearable data, and daily survey data from 23 Year 10 students, 6 teachers in 4 classrooms. For wearable data, we have temperatures, humidity, CO2 level, and sound data. For wearable data, we have accelerometer, heart rate sensor, electrodermal activity, and skin temperature sensor. For daily survey data, student participants submit their engagement-related responses and their thermal comfort-related responses. The prediction pipeline is as below. The physiological data and environmental data as an input, then we pre-process the data. And we first divide the sensor data into different class segments. Then we did the data cleaning, and then we drop out the low quality data through the visual inspection. After that, we extract a lot of features from multiple sensors. Then we did a nested cross-validation, and we applied light GEM regressor for the engagement score prediction. For the experiment results, The first table shows the prediction performance of the proposed multidimensional engagement model. Also, I explored the impact of different sensor combinations on the multiple dimensional engagement. Also, I identified some most influential features for different dimension of engagement. I also have some interesting findings. We found that I explored how different subjects affect student engagement score. Also, I found that students have the lowest engagement score in the afternoon, and when they feel formally comfortable, they have the highest engagement score. Yeah, that's all. Thank you very much.
Okay, thank you very much. Okay, I think we can proceed to the open discussion session. So I will ask kindly all presenters to open the cameras so they can be seen by our attendees. And I will go through the questions. So, okay. There are a couple of questions for Jean. So, are the households characteristics the same between the two cities? What explains the higher heating demand in Quebec?
Well, actually, in Quebec City, the city in the south of Canada, the heating demand was quite smaller than the heating demand of the building in Quebec. By a factor, I think like five times less heating demand in Quebec City than in Quebec. As for the household characteristic, if I recall correctly, they're mostly the same in terms of insulation, wall insulation, and efficiency in HVAC system. So both buildings try to achieve high energy performance. Of course, it's harder in the Quebec and in Nunavik to get lower heating demand, but from where I recall, I don't have the list of both household characteristics. They're quite similar.
Okay, so there is another question for you.
Yeah.
Recognizing that the domestic hot water and window opening differences you are observing between Quebec and Quebec City are based on a small preliminary sample, what do you think might account for them if they told for the larger sample? For example, differences in comfort preferences or typical behaviors? Very long question, so.
Yeah, I think that the difference in cultural preference and typical behavior can explain such difference. I think if you in the literature, we already see that there are differences in behavior from a country to another. So, Inuit people in the north can act differently than people in the south of Canada. Now, as I said, we are planning to convey interview workshop to get a better understanding of the typical behavior of Inuit people. And we already did some similar activities with our building from Quebec City. So we could compare maybe the result of the workshop from people in the north and people in the south to see if the difference in occupant behavior can be explained by difference in comfort performance.
Okay. We have a question for Alan. How do you overcome the privacy when you use normal camera to detect human term of comfort?
I'll try to see if I can interpret the question. I feel like the question might be the different modalities of data that are being collected through the webcam. So as I think the question might have hinted at, when you collect webcam data, you don't just collect, somebody's facial information. You collect information about the surrounding environments as well, like lighting, and then you could use, for instance, video amplification even to potentially get someone's heart rate information. So the way that we're treating that right now is any additional processing that is being done on a video would be counted as a virtual device. So the information that we gather about videos, we don't share with anybody. But let's say if you want to do some post-processing to collect thermal information or collect affective state or even let's say productivity status, then that's how we'll treat it. So it'll be counted as a virtual device inside the system. I hope that answers the question.
Okay. We have a couple of questions for Victoria. So the first one was related to a previous one. So it was related to set points. So if I interpret correctly, so were you able to normalize the impact of energy use with respect to these set points or changes of set points? Because the temperature seems very high, so probably they have been playing a little bit and rising.
But in reality, the temperature did not change much in the before and after. People want to live in this 25-degree paradise all year long, whether it's winter or summer. They spend a lot, as you would expect, they spend a lot of time in their houses, and they want to have these temperatures. And we have not done any remote control, even though these valves allow to, for example, set minimums or maximums remotely to give control the valve remotely. We have not done any of this. At the moment, we are only observing, and potentially we can implement different strategies of control, starting with the common areas and then going to flats where people should not be allowed. So somebody who is senile and so they won't be turning on and off, we can control them remotely. So that's one of the things that we are looking to do.
Okay, and then there is another question. When you adapted the new valve with blue and red arrows, did the digital interface remain or was it changed?
Yes, everything remained the same. So the thing is that even though when first looking at the valve, it looks very clear, the number, when you install it, the situation is very different. It might be behind the sofa in a corner, and the screen has very low brightness, and this is to maintain the minimum energy consumption that the valves have. They only have 2 AA batteries. So we kept it as it was. The main problem was that if you cannot see the screen, there is no indication on when to turn. If you turn it clockwise or anti-clockwise, does it come? Because it's counterintuitive. It is not like clockwise is up, it varies. So we thought adding the labels and also having the screen would give opportunity to use one or the other or both.
Okay. Yeah. Then we have a question for Nangao. Can you explain the engagement concept in detail? I don't know if we have enough time to explain it in detail, but maybe you can cite the methodology, the main references.
Okay. So to explain the engagement, in education, student engagement usually refers to the degree of attention, interest, curiosity, and involvement in the learning environment. Also, generally, student engagement is defined as a meta-construct that includes 3 dimensions: behavior engagement, cognitive engagement, and emotional engagement. Behavior engagement usually focuses on the participation and involvement in the academic or social activities, and emotional engagement focuses on the extent of positive and negative reactions to teachers or to the teaching content. Cognitive engagement usually focuses on students' level of investment in learning, includes being thoughtful, strategic, and willing to put efforts to comprehend the complex ideas in the class.
Can I just ask you, is this a standardized method for measuring something given by institution for education, or is it something based on literature?
Yeah, as engagement, it's a term in education, but I measure the engagement using the popular questionnaires from the education. They have some famous questionnaires to ask about students' different engagement. For example, they ask students, did you pay attention in the last class, or did you pretend to participate in the in the class, or do you enjoy learning this class? Yeah, ask such questions.
Okay.
Yeah, I asked 5 questions related to the engagement in the daily survey.
Okay. So we have a couple of questions for Maareva. The first one is how to measure the status of the louvers. So do we have some sensors that measure the angle of the openings of the louver?
We have about 70 sensors which are magnetic contacts that give information when an action happens, when the window open or close. So there is no specific time step. We have to choose a time step during data processing.
Okay. Yeah, probably the questions were related to the angle of. So you are just measuring open and closed, basically.
Yes, only open or close. We don't take into account the angle.
Okay, we'll jump to the other question. So mixed mode cooling would seem particularly valuable in hotels in locations like Réunion. What does your academic building study suggest for hotels and their occupants? So are there any conclusions that can be taken?
Good question. At the moment, I don't know, and I don't have any example of hotel operating in mixed modes. We don't study hotel with this study, but we need to be able to collect data to observe, to see how they work. And I know the challenge is obviously to extend this principle to other buildings.
Okay. Finally, we have another question for Victoria. You show 2 ways of adjustment. One is constant setting, and the second is time-dependent setting. Were there another strategy, for example, more indoor temperature-dependent adjustment?
Yes, well, this is something that we haven't done yet, but we are looking into doing. I was just showing these examples just to highlight some of the things that we think might be happening in the building, but in reality, we haven't done the full analysis yet. The data set that we have is massive and it's really great because so far we have 1 year. It's 80 flats and we have the information from each valve in each room of the flat. So bedrooms, lounges, hallways, bathroom, everything. And we are continuing the monitoring for another year more. So hopefully this is something that definitely we can look at the patterns and different profiles of interaction with the valves.
Okay, so we have another 3 minutes left if we want.
I have a question for Liam, if that's okay.
Okay, nice.
You're muted.
I muted myself once again. Sorry about that. So I was wondering if in your review, did you find any particular differences among countries or something that might be due to cultural or not?
Definitely. So the big one that was kind of eye-opening for me is one study did a comparison between Japan and the US and found that in Japan, rooms are heated and cooled 1 by 1. And in the US, houses are centrally controlled, as I said. So that makes a huge difference to the household energy. But I expect other differences in terms of prominent transportation methods, urban structure, in office buildings for the same reason as for homes, and so on. So one of the conclusions of my study, and others have noted this, is that we need multiple studies. It's not like we can answer the question for one city and assume it's universal.
Thank you.
Okay, so we are approaching the conclusion, and the next session is about case studies of occupant-centric modeling, design, and operation. So for all the attendees, you can join the next session via the link that is in the PDF that you received by email. I will kindly ask to the presenters of the next session if they can log out from this session and join immediately the next session. While for the other attendees, I will kindly ask if they can wait at least 5 minutes and then we join the next session, so 5-10 minutes, so on. The session will close now, and we hope to see you in the next one. And thank you very much to all the presenters and all the attendees for the question and your participation. Thank you very much.
Thank you.
Thank you. Bye-bye.
Thank you.
Yes. Thank you.
Yes, thank you. Bye.